more invited talk. Deepti, do you want to introduce while I set up everything?
Yes, so it's a great pleasure to introduce Professor Hima Lakkaraju. She is an assistant professor at Harvard University with appointments in both business school and the Department of Computer Science. She leads the AI for Life research at Harvard, and she has recently co-founded Trustworthy ML Initiative. Her research interests lie within the broad area of trustworthy ML. More specifically, it focuses on explainable, fair, and robust machine learning. So with that, Hima, please take it away. Give me 1 second. Let me unmute you.
Yes. Also, Hima, can you share your screen so that I can set up the view here? Okay, yeah.
Looks good.
Can I start?
Yes.
Awesome. Thanks so much for having me here and also for joining us today in this workshop. Today I'm here to discuss about some of our recent research on probing the disagreement problem in explainable AI. I think probably this is the last talk of the workshop, so I don't really need to motivate a lot about why we need to think about understanding machine learning models and how it can be sort of critical in various domains, particularly healthcare and finance and law and policy and so on, right? But just to give you like a couple of examples to sort of see the focus of today's talk. So why do we think model understanding can be useful? And I think Serena has already laid out the stage for this pretty well in the previous talk. So for example, let's consider
there is a disturbance, and is that a fan? Okay.
Better?
Yeah, that's better.
Okay, sorry about that. Yeah, so let's consider this scenario where there is a predictive model which is taking as input details about a patient and predicting if the person is at risk of COVID or not, right? So a doctor who is at the receiving end of the prediction, instead of just looking at the prediction, if he or she is also able to understand a bit more about the prediction, for example, what are the features that are being used by the model in order to make this prediction, then the doctor will have a better idea about if and when to trust these predictions, right? So in this case, for example, the doctor might notice that the appointment time and day are actually being used to make a prediction, and these are spurious features, and therefore he may not want to trust this particular prediction, right? So in some sense, explanations can help us or help decision makers determine if and when to trust model predictions when making decisions. And similarly, they can also help, sort of when thinking about the global picture of the model, some of which has also been touched by previous talks. For example, let's consider this particular scenario where there's a bunch of patient data, a predictive model which ingests this patient data and then make predictions. Now, if we also have some understanding into the behavior of the model, for example, that the model might be using features such as cold and cough symptoms to determine who is sick on the male subpopulation, and is actually relying on spurious features like ID numbers in the case of female population, then such insights can be used to even determine if the model is good enough to be deployed in the real world, right? So for example, in this case, the authorities, for example, like FDA or other regulatory agencies might see that the model is actually using spurious features on half the population, which is basically all the females in the data, and therefore it may not be ready for deployment yet, right? So given that there are several such use cases in terms of like, sort of explaining models or why explaining models can be useful, the next step to think about, and which is what has been the theme of this workshop, is to try and see how we can achieve model understanding, right? At a high level, there are two broad approaches to doing this. So one is to build models that are inherently interpretable. So for example, whether it is simpler models such as rule-based models or prototypes-based models or linear models and so on, models that are inherently understandable, one strategy is to build such models. Another strategy that has become popular in the past decade or so, past half a decade or so, is thinking about explaining models in a pre-built models in a post hoc fashion. And what do I mean by that is, for example, we may have black box models or complex models like deep neural nets, which we pass through an explainer algorithm, which in turn sort of breaks these models down into simpler and interpretable models that we can understand, right? So that has become, these kinds of post hoc explanations have become more popular in the past half a decade or so. And the reason why these have become popular is for two reasons. One is there were several recent studies which showed that in settings, especially with high dimensional data and large number of data points, there exist accuracy interpretability trade-offs, which means models that are actually accurate need to be complex and are therefore hard to understand, right? So they are not inherently interpretable. Furthermore, as a lot of for-profit organizations are developing proprietary models, a lot of times people like researchers or academics may not even have access to the underlying model. All you just have is a proprietary black box, right? So in such cases, we'll have to probe these models or use post hoc ways to sort of explain these models or understand these models. Okay. In today's talk, we'll be focusing on post hoc explanations, and particularly certain post hoc explanations, which are referred to as feature attribution based explanations. Okay. So the explanations that we'll focus on are actually local explanations, which means they are designed to explain individual predictions of any given classifier, right? It's a single prediction. We are trying to explain how the single prediction is being made. And these methods output feature attributions for individual instances, which capture the importance of each of the features on the black box prediction. And examples of such methods include lime, SHAP, vanilla gradients, gradient times input, smooth grad, integrated gradients, and so on. So essentially, all these methods output a vector of feature importances, which are then used to understand what features are playing a key role in the underlying model's prediction. Right? Okay, so the first part of this talk, I'll be focusing on some of the user studies that we did with practitioners recently. So the goal of these studies was to understand if and how often feature attribution based explanation methods disagree with each other in practice, and what exactly constitutes disagreement between explanations, and how to formalize the notion of explanation disagreement based on practitioner inputs, and how do practitioners actually resolve this explanation disagreement when they encounter it in practice. Okay. So let's try to get into the weeds of each of these. So first, what we did was, in one of our recent work, which is under review, we basically did 30-minute semi-structured interviews with about 25 data scientists who are using these post hoc explanation methods, especially the feature attribution methods such as lime and SHAP and gradient-based methods. So we asked them various questions about their workflow and how they use these methods and so on. And one of the things that kind of struck to us in their workflow was that several of these participants, 84% to be precise, said that they often encountered disagreement between explanation methods. And we got curious and we asked them, what exactly do they mean by disagreement between explanation methods? So they said that they have often observed that the top features output by each of these methods are different. The ordering among the top features is often different, and the direction of the top feature contributions, which is either contributing positively or negatively, is also different. And the relative ordering of features of interest is also different. Right? So they were sort of discussing that whenever they run two explanation methods in this category of feature attribution based explanations, they often see differences in each of these basic questions. And these kinds of basic questions are important important to folks like these data scientists, because they then have to communicate these insights to their clients or managers, and that is an important part. And now when they disagree, that's a problem for them, and they often seem to be like encountering this problem and also feeling frustrated about it, right? So again, these participants typically characterize this explanation disagreement based on factors such as mismatch in the top features, ordering of the features, directions of the feature contributions, but interestingly, not on the exact values of the feature importances output by different methods, right? In fact, 24 out of 25 participants in our study mentioned explicitly that feature importance values output by different explanation methods are not directly comparable. So in some sense, they seem to be having some implicit understanding that each of these methods is using a different technique to arrive at these feature attributions. So they are not expecting those numbers to match, but at the same time, the expectation seems to be that at a high level, they need to get similar high level insights from these different approaches, right? So when we ask a simple question, such as what are the top 3 features, they're expecting the methods to give similar answers. Okay. In fact, a lot of these interviews could be nicely summarized by this one quote by one of the participants, where they clearly mention that the values generated by different explanation methods are clearly different. So I would not characterize disagreement based on that, but I would at least want the explanations they output to give me consistent insights. And the explanations should agree on what are the most important features, the ordering among them, and so on, for me to derive consistent insights, but they don't, right? So this is clearly a problem that was echoed by several of these data scientists and further also being replicated in some of the other studies as well. So we took all these inputs and then we proceeded to formalize the notion of explanation disagreement based on the inputs provided by these folks. To this end, we came up with a bunch of metrics. So the first one that you see here is feature agreement, which basically measures the fraction of features in the top K features that agree between two given explanation. Right? So it's essentially the fraction of overlap in the top K features generated by two explanation methods for a particular point. And then rank agreement, not only should the features agree, we are not just measuring the fraction of the features that agree in two sets of top K features, but also we are looking for the rank within the top K to also agree, and that is captured by rank agreement. Then there is sign agreement, where we don't just say it's a match when the features agree, but we say it's a match when the features appear, when a feature appears both in the top 5 set of features for like two different explanations, but also the direction of the contribution or the sign of that particular feature matches, right? And sign rank is basically, it's not enough to just appear in the top 5. The relative rank within the top 5 should be the same. And also the sign or the direction of contribution should be the same. So that's obviously the strictest in terms of agreement measurement, right? And then we also kind of formalized two other notions based on, again, the inputs given by these practitioners. One is rank correlation. So whenever there are certain features of interest, we are taking those set of features and computing a rank correlation coefficient, like Spearman rank correlation coefficient on it, and also computing pairwise rank agreement, which is basically given a set of features, what fraction of those features have the same relative ranking, or rather, when you take them pairwise, which ones have the same relative ranking. So we are also measuring that in the pairwise rank agreement. Okay. So after quantifying all these insights into these kinds of metrics, we then carried out an empirical analysis with about 6 different feature attribution based post hoc explanation methods on 4 real world data set, a couple of them being tabular, one being text, and the other being an image data set, 8 different model classes, and we found several disagreements as explained by these practitioners between different explanation methods. Right, so here what you see are the results with 2 of the metrics, that is rank agreement and signed rank agreement, on the Compass data set with a neural network model. And as you can see, you observe a lot of disagreements. For example, if you see this, there's a clear disagreement between gradients and line, and so on. So you can see a lot of disagreements between different methods. Now, then what we got curious about was, okay, so given that these practitioners are actually encountering disagreement so much, what do they do when they actually see such a disagreement, right? To this end, we basically showed them pairs of explanations. For example, in this picture, you can see Lime and then Shap. And then we asked them if they think the above explanations agree with each other or not, and asked them why they thought what they thought. And then also ask them, if you believe these are disagreeing, which one would you pick? Which explanation would you pick and why? We just wanted to study how these people are resolving this disagreement problem when they encounter it in practice. And here for this, we did this online user study with about 25 users to understand how they're resolving these disagreement. So what we found was something very interesting. So practitioners said that they're choosing a particular explanation output by a particular method due to factors such as, there is more theory in a paper, or there is, the publication time of this paper is more recent, or even factors such as, oh, the explanation is matching my own intuition better, or just kind of saying, when the type of data is tabular, I'll probably use Lime and Shap. If it is images, I'm probably going to use gradient based methods. So as you can see, the reasons for choosing one explanation over the other seem kind of pretty ad hoc, right? And here are some quotes where they described why they are choosing certain methods. In fact, these are the most chosen methods. Colonel Shap turned out to be the one that people chose the most whenever they said there was a disagreement. And their arguments, for example, if you look at this, as Shap is a more rigorous approach in theory, right? And then smooth grad was the next best approach. And then again, they said, smooth grad is just newer or better. It's often considered an improved version of grad. So I'm going to use that. So I think those are the rationales that they're giving when trying to resolve these disagreements. So what we observed through this study is that these feature attribution methods often disagree in practice with respect to their basic insights, and practitioners are adopting ad hoc heuristics to resolve those disagreements. So now the thing to sort of think about is, why are these methods disagreeing? So what is exactly going on because of which we see these kinds of disagreements on the basic insights which practitioners want in their day-to-day tasks, right? And given that these methods are disagreeing, which explanation method should we choose for different kinds of data and applications? That turns out to be another broader question. Okay? And we started probing these questions a lot more in some of our recent preprints. First works that is currently under review, we asked this broad question of, why do these methods disagree, right? So what we showed in this paper theoretically is that various feature attribution methods, for example, Lime, kernel Shap, occlusion, vanilla gradients, gradient times input, integrated gradients, and smooth grad. All of these methods are essentially local function approximations. They're trying to find an explanation G which minimizes some expected loss with respect to the underlying function F within some neighborhood around X naught, around a given point X naught. Okay? But in spite of showing that there are some differences between these methods. And what are those differences? These methods adopt different loss functions and different notions of local neighborhoods, and this can explain their differences. So for example, what we found was that C-Lime, which is actually a continuous version of Lime. So essentially Lime, but you take each point and then you add some small Gaussian noise to the point to generate a perturbation. Whereas the actual method Lime, you binarize the data and then you try to sort of flip features with a value of 1s to 0, and that generates some perturbations, right? So yeah, continuous version of Lime, for example, the perturbation that it employs is essentially from a Gaussian with a 0 mean and then a small variance sigma squared, right? And then the loss function that it employs is actually a squared error. Similarly, smooth grad employs this kind of additive noise, which can also be modeled as a Gaussian. And then the loss function that smooth grad employs is that of gradient matching loss. and so on. So like essentially you are sort of seeing these differences in these methods because they're all trying to perform a local function approximation, but they're essentially using slightly different loss functions and then slightly different neighborhoods. So the loss functions are either squared errors or gradient matching loss, and the neighborhoods that they're considering, or even the perturbations that they're considering, can be additive or multiplicative, and they could be either sampled from a normal distribution or a uniform distribution or from exponential or Shapley kernels and so on. So those differences are explaining why we see different answers from each of these methods. Okay, so at least there is one unifying sort of framework to think about all these methods and the differences between them. Okay. And we also came up with this no free lunch theorem for explanation methods, where we showed that no single method can perform optimally across all neighborhoods, right? So that also kind of, takes us away from this notion of, is there one perfect answer to everything? Okay. So given that there are these differences between these different feature attribution based methods, and we also understand a little bit about why we see these differences now, now the question that comes out is, so which method should we choose, right? And one of the suggestions that we make in this particular work is that we can use a guiding principle based on the function approximation perspective. And that guiding principle could be that we choose a method which recovers the underlying model when the model is a member of the explanation function class. Right? So if you're able to recover the underlying model whenever possible, then that can be considered as a good approximation, since we are taking this function approximation perspective. And by using that guiding principle, we again show theoretically that for data sets which primarily have continuous data, we can use additive continuous noise methods, for example, smooth grad, vanilla gradients, or C-line, or modified multiplicative continuous noise methods, which are integrated gradients and gradient times input. And for binary data, primarily variables comprising of 0, 1 values, we can use binary noise methods such as Lime, kernel, Sharp, and occlusion. And under these conditions, these methods will actually recover the underlying model whenever possible. That is, when the model is a member of the explanation function class, right? Okay, so that's one way to look at it. That's one way to sort of think about it, which is, coming up with theoretical frameworks to analyze which methods can sort of work well in certain contexts or in certain data modalities, right? Another way to think about it is doing a lot of rigorous empirical evaluations of different properties of the explanations and then benchmarking them. Okay, and that's exactly what we are trying to do with what we have recently released called as OpenXAI, which is an open source framework to readily evaluate and benchmark post hoc explanation methods. Our current version supports all the feature attribution methods. We are working on a version 2, which is going to incorporate more other classes of methods, different other diverse methods, and so on. And the goal here is to basically come up with or carry out systematic, efficient, and reproducible evaluations of post hoc explanation methods on various kinds of data sets. And we have evaluation metrics that measure different aspects of explanation reliability. For example, faithfulness, for which there is a whole gamut of metrics, depending on if you have some ground truth or if you don't have ground truth. Stability, again, different notions, relative to how much will the explanation change relative to a small change in input. And how do you also measure the change in explanation relative to the change in the prediction probabilities or the internal representations generated by models such as deep neural nets and so on. And then also fairness, where we showed, and also I think Marzieh Ghassemi's group also had some recent work on this. And some of our recent work also shows that sometimes explanations could be generated in such a way that they are more accurate on one subgroup than the other, right? So that could potentially be because the underlying model is more linear, and you're probably doing a linear approximation on one subgroup versus the other, but still measuring these aspects can be useful so that explanations are not disproportionately accurate on one subgroup versus the other. Right? And most importantly, we also showcase these various leaderboards for different data sets to compare both existing as well as new methods, currently. So if there's a new method that needs to be added to this leaderboard, the process is very simple. Just kind of fill out a form and then link your code, submit your results and so on. And once we verify it, it can be brought onto the leaderboard. So we believe that this kind of transparent evaluation of post hoc explanation methods across various aspects of reliability can be extremely useful in terms of making more progress in the field, right? To conclude, so far in prior research, several methods were proposed to explain machine learning models, right? And I think at this point where we are with respect to the field and the directions of research that are emerging out there, it's important to characterize these methods and really understand which methods can be useful under what circumstances. And it is also very critical to bridge any knowledge gaps between researchers and practitioners so that these tools are not being used in an incorrect manner or an erroneous manner in practice. So with that, I think I'm almost out of time, so I'll stop here. And thank you so much again for your time. And here are some more resources on explainability.
Great talk, Hima. We have a question on Zoom for you while we wait for an in-person question. It's, does the no free lunch result assume a finite sample complexity?
I would assume that in the asymptotic regime, there is a linear explanation. Yeah, that's correct. Yes, it does. And yes to both those questions, Avi. You're right. Yeah.
Another question on Zoom is any overlap between packages Quantus and OpenXAI?
Yeah, so I think with respect to Quantus, I think the goal of Quantus is to put out those APIs out there, whereas OpenXAI is kind of starting with the goal of leaderboarding, transparent evaluation, benchmarking a lot more. And I think Quantus does have, I think there is some non-overlapping set of metrics, at least the fairness pieces are unique to OpenXAI. They are not available in Quantus. But I think I would say the goal of Quantus is to be a library that people can use, whereas the main goal of OpenXAI is publicly available dashboards and leaderboards comparing various methods.
That's good. We have another question on Zoom, but I want to see if there are any in-person questions first.
So far, no, so go for it.
Okay.
And,
so the next question is from a recent paper of Adebayo et al. They showed sometimes the XAI method represents the input data variation more than they can represent the actual ML model. Did you experience this in your experiments and have a probable explanation for this?
Yeah, so this is, I think, yeah, so definitely we did experience this in some cases, but whether we experience this in every case or prominently, the answer is no. But since we saw it in some cases, I think it would be valuable to go and dig into that a little bit more. But so far, I don't have a great answer for like, why does this happen, at least in some cases? But that's a great question. Definitely worthwhile thinking more about it.
Okay, so we have one question from the audience, and that's going to be the last question, and then we're moving on to the panel.
More than a question is a little bit a comment, maybe thought-provoking, but I also want to hear what you have to say. So regarding the question of what is my take on which method or which post hoc method should be taken or used, I would say none. The reason is that by and large, we want explanations that are cause and effect, and no model that is just based on computing some gradients and looking at regions of the image and then trying to figure out what they meant is ever going to achieve that. I think what you said at the beginning, which is that we should instead build machine learning models that are explainable by construction rather than trying to explain them post hoc, would probably be the way to go.
Yeah, I mean, my 2 cents on that is definitely if there is a means to sort of build a model that satisfies your requirements of interpretability to begin with. And this model is inherently interpretable, accurate. So it's checking all your boxes in that sense. I think that is probably the way to go. So there is, I would say, there is nothing very, as I also discussed in my talk, sometimes it can so happen that you're just dealing with a black box, or you have constraints of, okay, I can build this model to be accurate, but somehow I'm not able to achieve interpretability alongside inherently. So here is another way, right? So I think more than this being for lack of a better word, a political issue, essentially what predictive models are doing are approximating the ground truth, right? So that they are function approximations for, input features and then the ground truth. And what local explanations or post hoc explanations are doing they are like a next level approximation. They're trying to approximate the behavior of the original model, right? So in some sense, if you can get the original model, keep it interpretable, do it, right? But if for some reason, if that's not happening, then the next cut is to basically approximate those using whatever information you have available. So I think it's almost like a context dependent issue than, like should one side win versus the other, but that's just like my take on it. Essentially, they are function approximations, right?
Okay, let's thank the speaker once again. Thank you, Hima. This was a great talk. Now, the next thing is panel. Let me just share the screen while I speak. So we're going to do like an hour-long panel led by me, Dipti, and Devi. But before that, I think we can all take like a 10-minute break or something like that, or let's make it 15. So let's meet at 5 p.m. So that I have time to set up the equipment and the table, and let's start the panel discussion. It's going to